Hello everyone, I am Radhika, and in this video I will take an example based on supply independent biasing and degenerate points. In this example, we are assuming that lambda is not equal to 0. We are taking channel modulation effect and estimate the change in I out for small change del VDD in the supply voltage. So this is the figure we have already taken in the case of supply independent biasing. So first we will replace the transistor whose gate and drain are connected as a resistor. Okay, in this case and in this case. Converting them to a resistor. So in this case it is turned to R1 and in this case it is R3. So basically R1 is equals to RO1 in parallel with 1 by GM1 and R3 is RO3 parallel with 1 upon GM3. We calculate the gain from VDD to I out and the small signal gate source voltage of M4 equals to minus I out R3. Okay, this is the in this branch the current is I out and the voltage drop will be I out R3. Similarly, both are parallel. So in this case also gate source voltage of M4. The gate, this is the gate and this is the source. We already know that in PMOS, the source is at higher potential. So in this case, the current will be in this direction. So there is a minus sign and minus of I out R3. And the current through RO4, the current through this RO4 is VDD, that is VDD, this voltage drop minus this voltage drop, VDD minus Vx, this point upon RO4. This is the current going through this RO4. So thus applying a simple this KCL across this loop, we will get VDD minus Vx RO4 current through this branch plus I out R3 GM4, that is this thing, I out R3 GM4 equals to Vx upon Rn, that is this point, Vx upon R1. Okay, so this is simple a KCL equation. Now, if we denote the equivalent transconductors of this M2 and RS, this M2 by GM2, we will get the I out by Vx, and then we can get I out by VDD is equals to 1 upon RO4, 1 upon GM2 RO4 in parallel with R1, this R1 minus GM4 R3 whole inverse. So this is the simple equation which estimate the change in I out for a small change in VDD. Next, we will consider the degenerated points. As we have seen in some application, the sensitivity is large because of various capacitive paths. The supply sensitivity, this sensitivity of supply on the current output current rises at high frequency due to this capacitive path. For this reason, we drive the supply voltage from the locally generated, that is less sensitive voltage, as they will not rise at higher frequency. So there is an important issue in supply independent biasing is the existence of degenerate bias point. So let us again look at the circuit of this figure A. We will find that if all the transistors, these transistors carry zero current and supply is turned on, VDD is on, they remain off indefinitely because the loops can support zero current in both the branches. And uh, this point is not covered the in the equation we have derived for I out. So let us take this case of degenerate point bias point. How can we eliminate this degenerate bias point in our circuit? So this problem can be resolved by adding a mechanism that drives the circuit out of these degenerate bias points when the supply is turned on. So it is shown in a figure where a diode connected device, it is known as a diode connected device at the gate and this drain terminal both are connected. So this diode connected wire M5 provide a current path from VDD through M3 and M1 to ground upon startup. So M3 and M1 cannot be off. M3 and M1 and M2 and M4 cannot remain off. Of course, this technique is only practical if the M3 and M1 and this is and hence M2 and M4 cannot remain off. For this and this technique is practical only if the threshold voltage of the transistor 1, transistor 5 and transistor 3 is less than VDD, because we are considering that the supply is on during the time of startup and the threshold voltages of these devices should be less than that of VDD, and VGS1 plus the threshold voltage of VTH5 plus VGS3 should be greater than VDD, and this is done to ensure that M5 will remain off after startup, because M5 is the device which is only connected to provide a current path from VDD to ground upon startup, and it will be remain off after startup. So this is the illustration of degenerate point. How this VDD, when VDD is on, the current is also zero throughout the branches, as it offer a zero current in both the branches. Okay, so this is a simple demonstration of the degenerate points, or we can also known as startup points, and this is a startup device. How we can eliminate this degenerate point. Okay, thank you.